All right, so this is what we did on Monday. And instead of going through and like doing out the entire proof and everything else for the thing I'm going to show you in a minute, I wanted to look at this. So we went from this, did the whole limit definition equation that we did, and got that. So there is a rule that allows us to go from that to that without having to do all this extra work. Okay. It's known as the power rule. So in differentiation, there's a bunch of rules that we're going to look at. They're all basically shortcuts to doing this limit formula. Some of them I will show you out and I will prove out doing the limit formula out so you can see exactly where it came from. I'm not going to do it for the power rule because we literally just did a bunch of these problems on Monday. So you've already seen that process work. So these are the first two things you need to write down. So the first one is the derivative of a constant is always 0. So if you think about it, what is the derivative giving me? What were we finding on Monday? Slope. We're finding slope of whatever that line was. So if a function is constant, so y equals 2 or y equals 5, what's the slope always going to be? 0, because it doesn't change, right? So the derivative of a constant function makes sense because that's the slope of a line. The power rule is what we were just looking at a second ago. We had x to the third. The power rule states that I'm going to take this number up here and bring it down in front and subtract 1 from the top. So this becomes 3x to the second. So you're always going to take whatever the exponent is, move it down in the front, and subtract 1 from the exponent. That's what the power rule states to do. That's what that says. Bring the exponent down in front and subtract 1 from the exponent.
That's why just x cut.
Correct. We're going to do that one in a second. All right, let's look at a few. All right, so if f of x equals x to the 7th, what's f prime of x equal? 7 x to the 6th. Taking that exponent up front, up top, moving it down in front, and subtracting 1 from it. So h of x equals x to the 100th. What's h prime of x? 100x to the 99. Now, what I even said this on Monday is I'm going to show you all this stuff and we're never going to use it again. The reason we did that is because if I literally just said, here's this rule, you'd have no idea why. Okay, you could do it, you could find the rule, and you would get the right answer every single time, but you wouldn't understand why it represents the slope. Okay, and that's what we were trying to do that's the entire purpose of Monday's lesson, was to get you to understand that the derivative is a slope. Okay, and now we're going to look at rules that makes our lives easier. Okay, so while it's a bunch of rules and they get a little more complicated as we go on, it's not the actual rules aren't the difficult part. It's making sure that you can actually plug it in correctly and do the problems out. So these first couple problems are pretty easy to do. Let's get one more. Which g of x to x equals x? What's G prime of X? Huh? Why? Why?
Because the slope of a y equals x. Which is one.
Okay, that's a better answer. Okay, so let's use the rule that we already know. Okay? So the exponent in this is a 1, right? We bring it down, and we subtract 1. So you get x to the 0 power. What's anything raised to the 0 power? 1. So that's just 1. Okay. So sometimes you have to understand why it's true. Because like the same concept of anything raised to the 0 power is 1. Why? And I know for utter fact that you all asked your math teacher that in high school when they said that. Because every one of my students always did. Because it doesn't make sense. Okay? Like every other thing makes sense. If it's 2 to the 3rd power, it's 2 times 2 times 2. If it's 2 to the 4th power, it's 2 times 2 times. Okay, 2 to the 0 power is 1? I have no 2's. Why is it 1? So it's like, then they have to go through and show it out. So using the information that we know to be able to find it makes our lives easier to do. So even though we're saying that anything that if it's just X or just whatever letter, it's going to equal 1, it's because the power rule exists and the power rule still works on it. Okay? What about this one? I want to give everybody a chance to think because I know you know the answer. So yeah. Yeah. So the power rule is still going to work. All right. This power rule stated it works for any real number. -3 is a real number. The rule stays the same. So I bring it down and I subtract 1. -3 minus 1 is -4. Okay. Same rules apply. Okay. Not that one yet. Slide first. How about this one? Okay. Good attempt. We're actually going to learn rules about products and quotients. So this would actually end up being the quotient rule the way, but do I really need to do the quotient rule for this? Yes. This is where your algebra comes in. Okay. You want to try simplify the problem down as much as possible before you try to do the actual calculus part, the derivatives. X to the 4th over x to the 7th is what? 1 over x to the 3rd, because it's on the bottom, or x to the -3rd, which is exactly the same problem we just did. That ends up becoming -3 x to the -4th, right? Or -3 over x to the 4th. You typically don't want to have negative exponents in your answer at the end. You can use them in the middle problems to actually do the problem out, but you don't want them at the end. So this would be the final answer.
is pretty bad. You know, while X was still in the denominator, like we tried to apply the.
So if you did so what would you have done? If you had done it like this, so if we looked at just this and did the power rule from there, right? What would you have gotten?
The X.
Is that what the answer is? Yeah. So the power rule doesn't have a division in it. It is straight. The variable's got to be on the top. So if it's in the bottom, I need to bring it up top to be able before I do the problem. So that doesn't work because it doesn't come out to be the same answer. And the same thing with trying to do it, splitting it up. If you had gotten 4x to the third over 7x to the sixth, not the same answer. Okay. What about this one? Do I have an exponent for this problem? What is the exponent? Right. So we have to remember that the square roots becomes that. So now what's my derivative of it? The rule still applies. So where's that 1/2 going? Right in front. And then I do subtract 1 from that 1/2, and I get what? Negative 1/2. So then this problem becomes 1 over 2 square root of x. Yes.
In future tests and stuff, are you okay with us leaving radicals in the denominator? Or do you want us to simplify it?
You don't necessarily have to do rationalization for these.
Use that for finance again.
Oh, I can keep doing the derivative. So actually, remember we did. Remember we talked about this on Monday, right? We have first derivative, second derivative, third derivative. So you can keep doing the derivative. So that right there was the first derivative. We could do it again, find the second derivative. We could do it again, find the third derivative. Actually switch over this for another reason though, because there's the problem that we just did now that we did on Monday. That's the square root of x. And notice we got 1 over 2 square root of x. So those rules just help simplify down that. So the limit came first, and then they were able to use that to prove these rules always work. They didn't always work, we wouldn't use them. All right, a couple other quick rules before we go on to some other problems. And these are pretty straightforward. If there's a constant in front, just like if there was a constant in front of a limit, I can pull that constant out and just work with the one with the variable. So the same thing in derivatives. I can pull that constant out and still work with it. The next one is sum and difference. If there's an addition or subtraction between them, not multiplication and division, addition and subtraction, I can split them apart and do them in pieces. Okay? So these are both obvious rules. But again, we have to state them because they're not always true. Like we can't just split up any arithmetic operation. So you can't split up multiplication and division. We can only do the addition and subtraction. So they have to be stated. But these are ones that you typically are not going to write out. You're just going to do them along with the power rule. Okay. Yes. Oh, I'm going to in a second. Yeah. No, that's fine. That's literally the next thing I'm going to do. We're going to do, actually, there's only one other rule I'm going to show you today. Everything else the rest of this class today is literally just doing problems. All right. Let's look. All right. So we've got f of x equals 5x to the sixth. So the constant rule at the top states that I can look at this as 5, and then I can do my derivative of x to the sixth. Remember, d dx means the same as taking the derivative. So what's the derivative of x to the sixth? 6x to the fifth, right? So the answer will be 30. X to the fifth. So the constant doesn't change the power rule. We just have to multiply the whatever we get by what that constant is. So we're looking at the 3/4 goes out in front, and then it's d dx of x to the 5/4. So what's the derivative of x to the 5/4? Yep. So my final answer is 15/16 x to the 1/4. So while fractions make them look harder, the process is the same. Okay. And get comfortable with fractions, especially with exponents, because that's your roots. So x to the 1/4 is really the fourth root of x. Okay, so those are things that do come up quite often.
Would you rather us write it as like the fourth root of x?
Either way, it's fine. No, that doesn't matter. I think it's easier to write the square root than x to the 1/2. So I typically write those, but the other ones,
Yeah.
it's fine. Even x to the 1/2 is fine. It's more important that you know you can go back and forth between them depending on how you want to look at the problem. Because a lot of times they will write the problem with the root in it and you have to change it to the exponent. Rarely are you ever going to see a problem just as what's the derivative of x to the third? things like that. Most of the time, you're going to see polynomials that you're going to have to work out. Okay. So in this situation, now we're going to use that sum and difference rule. We're going to split this up into pieces. So f prime of x equals 5 d dx of x squared plus d dx of x minus the d dx of 3. This is that sum and difference rule. So what's the derivative of x squared? 2x. So that's going to be 10x. What's the derivative of x? 1. What's the derivative of 3? 0. So there's my answer. So the derivative of 5x squared plus x minus 3 is 10x plus 1. What's the second derivative? It's just 10. Because we just do the derivative of the derivative. So what's the derivative of 10x? The x is 1, so it's just 10. What's the derivative of the 1? 0. What's the third derivative? It is 0. What's the fourth derivative? Still 0. 0 is a constant, right? So the derivative of 0 is still 0. Okay, so you're asking, can we keep going? Yeah. So you run out of problem. Run out of exponents. Yeah. The derivative of a constant is 0? Oh, derivative of 3 is 0? If y equals 3, what's the slope? Right, that's why. Because remember, derivative is just slope. So since 3 is a constant and the slope never changes in that, it's 0. And that's why even like the derivative of 10 is 0. Yep.
In the problem, the constant's just adjusting where it is on the graph. It doesn't affect the slope.
Correct. Yeah, it's just shifting it up or down. So that's just shifting your y up or down by -3. So it doesn't really change the slope of the problem. That's why it's not used. All right, let's you guys do one. All right, find me the derivative. That's all you're gonna need to do. You do not need to write out like this whole step. Unless you want to. Okay. That's the power rule. And the -5 goes to 0. So you don't have to put the plus 0. Simple enough. You now know calculus. Let's do. Do
May have said this before, but why do you subtract one from the exponent and take the derivative of it?
That's the rule. It's the way it works. If you look back at what we did on Monday, if you look at the problem that's x to the third minus x, and you walk through like the steps that we did, it ends up working out that way. If you look in the book at the beginning of the section, they actually do prove it out with the limit rule. I just used the problem that we did on Monday to show it to you.
Two F minus one or -1 minus is 2F.
No. Can we do it the way it's written? We have to rewrite it. So that's m to the -1 plus m to the -2. -1 comes down. -1 minus 1 is -2. -2 comes down. -2 minus 1 is -3. So now we have -1 over m to the second minus 2 over m to the third. That's your derivative. This is why we say all the time that the calculus rule is the one that's going to mess you up. Because I'd be willing to bet most of you could subtract and that piece fine. It's manipulating the problem to be able to do that that's going to cause you the problems. Let's do this one. Huh? Yeah. Okay. All right, try this one. Correct. When you're writing your work, if you want to make sure that you remember where the thing goes, a nice little habit to get into is putting a little line down. That means, okay, I know the W is not in it. A lot of times they'll always write the stuff in front of the square root. The square root will be at the end for that reason as well. So, but the book doesn't always follow those conventions. So. So what's the derivative of the square root of 2w? Just the square root of 2. Because the w becomes 1. And then the minus square root of 2 is 0. So the answer is just the square root of 2. Square root of 2's, things like that, those are constants. They don't change your rules.
Why do you only by one? There's one greater.
So w, if we just look at w, so f of w is w. The exponent's 1, right? So the 1 comes down. 1 minus 1 is? What's w to the 0 power?
One.
Right. So that w becomes 1. Square root of 2 is just a constant. It'd be no different than it was 2w. The answer would have been 2. So that's the thing. You got to remember that the square root is a constant. All right, this one. What's pi?
Pi.
It's pi. It's a number. It's a constant. So it doesn't affect this problem at all. It's just there to annoy you. Okay? Don't let crazy things annoy you. Focus on the rules. Yep. Do some algebra here. Remember, square roots, you can split them up. As long as it's multiplication. So this is now just a constant times a variable, no different than we've done in the last couple problems. So the square root of 2 stays. The x to the 1/2 becomes what? 1/2 x to the negative 1/2, right? So I end up with square root of 2 over 2x to square root of x. If you rationalize it, you end up getting square root of 2x over 2x. So sometimes, yes. This one, I don't want the negative exponents. If you moved it down the bottom and left it as x to the 1/2, that's fine. But don't leave negative exponents. I'm gonna do that one. Let's do that. Yeah. I'd still have a 2 down the bottom. Because the x to the negative second can go up top. But the 2 would. And then I'd have multiplication instead of division. So you'd still have to worry about that stuff. How can I split up a fraction? If the addition's on the top, I can split this up like this. So this becomes 1/2 x to the negative second plus 5/2 x. So when you're looking at the power rule is out of all the rules that you're going to learn throughout actually all of calculus, the easiest one. So the more, if you can manipulate the problem to be able to use that over some of the other rules, it's going to make your life easier. Okay. But you have to be comfortable with the algebra to be able to do the manipulations. So we got what? 1/2 times negative 2x to the negative third plus 5/2 times 1. So we've got -1 over x to the third plus 5 halves. That's my final answer. Can I split that? Can you split it if it has addition on the denominator? No. That one I can't do by the power rule. We need to use something else. So as of now, you can't do that problem. Can I split that apart? No. You can split multiplication, addition and subtraction under a square root. Okay.
Um, we should do it.
So we don't currently have a rule that allows us to work that moves out of square root. Because the square root's an exponent. And if I did, then I would just basically I'll be just doing the square root of the Ferraro rule to x, because the exponent can be pulled out, which wouldn't make much sense. So right now, we don't have an ability to do that problem. You will, just not right now. Okay. So there is a limit to what manipulation that we can do. Can we do this problem? Can we do it as it sits? We have to FOIL it out. If we FOIL it out, then I just have addition and subtraction. Okay, so FOIL it out. Once you FOIL it out, find me my derivative. All right. How confident are we feeling with the power roll? Good? All right. Let's start doing some applications of it. The 3 comes down in front. 3 times 15. It's the same thing. This, you can't. You can't find the derivative of that because we don't have a rule that finds the derivative of multiplication. That's next class. But what you're going to see next class, we're going to actually talk about the product and quotient rules. And a lot of times it's easier to FOIL it out and get the answer with the power rule than to do the product rule if it's a simple problem like this. Okay, so you will have multiple ways to do certain problems. You'll have to decide which one is best for you to do it. All right, so here is, I want to find the points of the curve for that. Oh, there we go. So we have y equals x to the third plus 3x squared minus 9x plus 10. I want to find out where the tangent line is horizontal. What am I looking for? The tangent lines are basically my what? They're my slopes that come up. So yes, it's the derivatives. So I'm going to find the derivative. And I want to know where they're horizontal. So I want to find where my derivative is what? 0. So step 1, find the derivative. And then step 2, set that equal to 0 and solve. Yep. Never had a factor. This one was nice because you could pull out the 3, so you didn't have to worry about doing like the AC method or whatever. However method they've taught you how to do that. So this one comes out to be x equals -3 and x equals 1. So we know that the tangent line is horizontal at that point. What does that mean about my original problem?
Those are like the peaks,
Why?
because they're doing they're, they're the quarters, because at quarters, it's 0.
So the graph changes direction.
Yeah.
So those would be your mins and maxes. Maybe not absolute, depending on the problem, but they're going to be mins and maxes. And if we look at this graph, we see that those are the mins and maxes. And in this problem, I have a maximum of 2. And if you plug those numbers into the problem, you can get the exact values of those. So the 37 and the 5. You'd want to plug those values back into the original problem, not the derivative, because if you plug them into the derivative, you're going to get what? 0. Okay. And if you look at before the point of -3, my slopes are positive. The graph is increasing. After that point, my slopes are negative, which makes sense on why the derivative crosses at 0, because at one point it's going to be positive, one point it's going to be negative. So if we graph the derivative for this one, there we go. I need to do something wrong. If we graph the derivative of this one, we can start to see how it's got my zeros at those points. And now we can also tell that between -3 and 1 is the only point on this graph where the graph is decreasing. It's a negative slope. So that derivative is going to give us a lot of information about that graph. All right. This one. Find me the equation of the tangent line at 0.23. So what are the two things I need to know for my tangent line? I need my slope and my y-intercept, right? All right, so find my slope. That's the derivative. Remember, always pull your exponent, your variables up top and work through it. What's the, how do we find the slope now at that point? That is the slope of the entire equation. I want the slope when I'm looking for my tangent line. So I need to find my slope at 0.23. We're going to plug the 2 in for x. That will find my slope at that point. So my slope at that point is 1/2. You get 3. That's not giving me your slope though. Right, but you need to find your slope. That if you plug 2 into the original problem, you're gonna get 3. That's the point on the graph. I want to know the slope at that point. So remember before you'd have to find 2 points on the graph and then average out those 2 points. But with calculus, we now actually can find the slope at a specific point. That's why we did the derivative. This is the slope at any point on that graph. I want to find the slope when x is 2. So I plug that 2 into the derivative slope, and that gives me my slope at that point. Now I need to do my y equals mx plus b. To find my b, I plug in my 1/2, my 2. So b is 2. So my equation is y equals 1/2 x plus 2. All right. Can I use the power rule on this? What did the power rule state? What was the one qualification? The exponent has to be a real number. Is x a real number? No. I could do x to the e. I could do that. But I can't do e to the x. This is an exponential function. Okay? So I can't use the power rule for this. All right, so let's go back and use the wonderful limit rule that we had. So let's do the generic one. We're just going to do e to the x, because now b can be anything, including e. Because remember, e is just a number. So I have the limit as h goes to 0 of f of x plus h minus f of x over h. All right. So let's try to simplify this. So remember when there's addition to the exponents, what does that mean? How can I split that apart? The bases are the same. I'd add the exponents, right? So if I add the exponents, I can split it apart and just do it like that. So this became that. So now I can pull out a b to the h or b to the x, and I have bh minus 1 over h. Because there's a bx in both the pieces on the top. Oh, it's not. It's just h was from the top. Does the limit affect that at all? Is there an h in it? No, in the bx. No. So I can take that out because the limit doesn't impact it. So I'm just looking at the limit as from h goes to 0 of b to the h minus 1 over h. Now this right here is just my derivative, right? That's what we've been looking for. So this is this derivative at where x is 0. Remember, it's just that's the definition of the derivative, right? It's that f of x minus h or x plus h minus fx over h. Can I do that limit? No, because if I plug in 0, it's going to go b to the 0 is 1, so 0 over 0. So the only way to look at this is to actually look at it either numerically, because there's no way to simplify that one down. So we have to kind of look at this numerically. So let's look at it. All right. So if we look at this graph, yeah. Oh. If we look at this graph, we're looking at it at 0. That's the value that I want to look at. So if b is 2, we're at like 0.7. If I set b to 3, now we're above 1 somewhere, right? So at some point between those two values, the limit has to be what? At 3, it's wrong graph, this one. 1.09. And at 2, it's 0.07. So at some point between those two, it has to be 1, correct? Why is that important? Because if at some point that red box is 1, then this would equal just b to the x, correct? Because b to the x times 1 is just b to the x, right? So the question is what number between those? So it's closer to 3, right? All right, so let's come down from 3. Let's do 2.9. It's getting closer. Oh. So if we start off at 3, not 23, we're right about there, right? So 2.9, we're getting closer. We're getting closer. It's just below it. That's above it. If I set the limit to approach 1, I'm not looking at 0, though. So what's E? So what this showed is that when B equals E, my derivative, so if f of x is e to the x, my derivative is also e to the x. So the derivative of e to the x is e to the x. It's only when it's e. Any other number, there's something else in front. Okay? If it's e to the x, it's e to the x. Yeah. What, to find the other ones?
Yeah.
We will. Not yet. So for right now, you just are going to know the e to the x one. What's the derivative of e to the x? What's the derivative of x? That's your derivative of e to the x minus x.
Oh, sorry.
That's okay.
Thank you.
I was trying to kick it back to you. 3 e to the x minus the x squared. And the x squared is going to be 2x. Remember, the constant rule states I can pull that constant out. If it wasn't a constant, if it was x, then I would not be able to do it. But constant rule states I can just pull the constant out. All right. Let's do one more. Let's actually we'll do two more problems. I'm going to do an e to the x one. Yes. What's the derivative of one? Okay, so really the only thing we're worrying about is that, right? What did we do when we had addition up in the exponents? We split it up. So that e to the x plus 1 is e to the x times e to the 1. Which is just e times e to the x. E to the x is just e to the x, and e is what? E is just a constant. So this is literally just going to end up being e to the x, or going back, e to the x plus 1.
How long that is?
Yes, that does not always work. So if we had e to the x squared plus 2x, for example, I could split that up as e to the x squared times e to the 2x, but neither of those are constants now. And neither of those has pluses to be able to break them down any further. So this, as of right now, you can't do. Okay, but since this one was x plus 1, it works out that way, yeah. All right, last problem. I forgot to do it before I did the e to the x problem. So position, they give you. How do I find velocity? That's my first derivative. So what's the first derivative? 3t squared minus 3. Now you can start to remember what I said at the beginning of class, that calc-based physics is a little easier. We can find instantaneous velocity. We can find instantaneous acceleration. Without the calculus, you have to kind of force your algebra to do those types of things. Acceleration is what? Yeah, it's the derivative of your velocity or your second derivative of your position. So what's the derivative of 3t squared minus 3? It's just 6t. After acceleration comes jerk. And that's just the third derivative. So what's the acceleration after 2 seconds? 12 meters per second. Yeah. Okay. What's the acceleration when the velocity is 0? What's the acceleration when my velocity is 0? Is it?
Acceleration is slowing down or speeding up.
Right.
So it'll be negative 3.
So, well, step one, we have to do what? We have to figure out where our velocity is 0. Right? So that's the first step. So 3t squared minus 3 equals 0. So t squared equals 1. So t equals plus or minus 1. So my velocity is 0 at 1 second. So then what's my acceleration at 1 second? 6 meters per second. So if we look at this, here's the graph. So the green is the position of my function, or position of my particle. The purple is my velocity. So when my position's at 0, my velocity is at negative 3 because we're going down. When my velocity is at 0, I have my low point in my position. but my acceleration is still 6. Because basically, you're pulling out of the dive. So at one point, your velocity is going to be 0, but you're still accelerating to pull out of that dive. Okay, that's one way to think about it. Because you're right, when you think about it, it's like, okay, if my velocity is 0, how am I accelerating? Well, at some point, you're going from negative, you have to switch and go positive. So that takes energy. So, and that's what your acceleration is. Okay? That's it. You can drive your physics teacher nuts by actually using your calculus to do your physics stuff.
Last professor.
Good shit.
I